In this lecture, we're going to review some of your first year material on vector algebra and kinematics. So I've given you some definitions here that you'll have already seen in your first year courses. We have the definition of a dot product, a cross product, and the triple product of three vectors. Let's start off with a couple of facts that you'll remember from your previous courses. First fact is that the dot product of two orthogonal vectors is 0. Let's take a look at an example of that. So we've got two vectors here, v and w. I've expressed them here both in column notation or in I, j, k notation. Of course, those two things are completely equivalent. So we're going to prove that v and w are orthogonal by taking their dot product and showing that it's 0. So the dot product is just multiplying together the corresponding components of the two vectors and adding up what we get. So I'm going to use the column notation here because it's particularly easy to calculate dot products in the column notation. Writing my vectors as columns. So you see I just multiply together the corresponding elements of each matrix. So I get 2 times 1 plus minus 1 times 8 plus 3 times 2. And that's going to be equals to 2 minus 8 plus 6, which is 0. And because the dot product of these two vectors is 0, that implies that v and w are orthogonal. Likewise, if I know that v and w are orthogonal, their dot product will be 0. So it goes both ways. So the next fact we're going to look at is that the cross product generates a new vector that points in the orthogonal direction. We're going to calculate the cross product of u and v, so u cross v, and we're going to check that the resulting vector, we'll call it w, is perpendicular to u and v by using the dot product, by using the fact that we just have shown in example 1. So let's first of all calculate our cross product. So I've got w is equal to the cross product of u and v. So I can calculate that cross product by writing out a determinant of a 3 by 3 matrix, where the first row of that matrix are our unit vectors in the x, y, and z direction, I, j, and k. The second row will be made up of the components of u. So the components of u were I plus 2j plus 4k, so the components are 1, 2, 4. And the third row is made up of the components of v. So those are given by 3, 5, and 1. So we have this 3 by 3 matrix to calculate. Its determinant will be given by I times the determinant of this 2 by 2 matrix so that will be given by 2 times 1 minus 4 times 5 minus j times the determinant of this 2 by 2 matrix made up of these two columns. So I've got 1 times 1 minus 4 times 3 plus k times the determinant of the bottom left-hand corner 2 by 2 matrix. So I've got 1 times 1 times 5 minus 2 times 3. So for my I component, I'm going to get 2 times 1 minus 20, which is minus 18. My j component, let's not forget that factor of minus 1. We've got 1 minus 12, which is minus 11, and I've got a factor of minus 1, which gives me 11, plus k vector times 5 minus 6, which is minus 1. So my vector is minus 18i plus 11j minus k. So we saw that the cross product gave us a new vector, w. So we need to now show that that new vector is perpendicular to our original vectors u and v, and we'll do that using the dot product. So the dot product of u with w should be equals to 0, and the dot product of v with w should be equals to 0. And that tells me that w is now perpendicular or orthogonal to both u and v. So let's check that. So u is given by I plus 2j plus 4k. And we're dotting that with w, which we've just calculated, minus 18i plus 11j minus k vector. So I've written here the dot product in terms of ijk's this time. So multiplying together the corresponding components gives me 1 times minus 18 plus 2 times 11 plus 4 times minus 1. So that's going to be minus 18 plus 22 minus 4, which is equal to 0. So that implies that u and w are orthogonal. Let's do the same now with v. So v dot w. V was given by 3, 5, 1. So I'm going to have 3 times 8 minus 18 plus 5 times 11 plus 1 times minus 1. So that will be 54 minus 54 plus 55 minus 1. And that also is equal to 0, which implies that v is perpendicular or orthogonal to w. So I've used a shorthand notation there for orthogonality. So we got u is perpendicular to w. So we saw that the cross product ended up giving us a vector w that was perpendicular to the original vectors. Now, what does the cross product actually mean? Well, you've seen in your first year notes that the cross product, the magnitude of the cross product, is the area of a the magnitude of a cross product is the area of a parallelogram with sides u and v. Likewise, the magnitude of the vector triple product is the volume of a parallelepiped with sides u, v, and w. So let's see an example of that. So here we're given 4 points, P, Q, R, and S. Those define 3 vectors, P to Q, P to R, P to S, and those define a parallelepiped. So we want to find the volume of that parallelepiped. So let's draw a quick sketch of what we're looking at here. So we've got points P, point Q, point S, and a point R. So here's our P, Q, R, and S. Those are points in 3 dimensions. I'm going to use those to define 3 different vectors. I've got the vector from P to Q. I've got the vector from P to S. I've got the vector from P to R. And that then allows me to define a parallelepiped. Where all of those faces of that shape are parallel to one another. Okay, so we want to calculate what the volume of that shape is. To do that, we're going to calculate the scalar triple product, the vector triple product, excuse me, of these vectors. Let's call the vector u being the vector from P to Q, the vector v being the vector from P to R, and the vector w from P to S. So let me write that out. So u is the vector from P to Q, and we remember that when we're calculating vectors from directed line segments, when we have a vector as a line from P to Q, what we do is we take the coordinates of Q and subtract the coordinates of P. That is, we write it as OQ, that's the coordinates from the origin to Q, so that's the coordinates of Q, minus OP. So that'll be referring up here to the coordinates of our points. It'll be 0, 1, 6 minus 3, 1, 1. So that'll be so that will be minus 3, 0, 5. Our vector v is given by the line segment from P to R. So again, it's going to be the components of R minus the components of P. That will be 2, 4, 6. And our vector W will be the line segment from P to S. So that'll be the components of S minus the components of P. So we've got our 3 vectors here. Now we need to calculate the vector triple product, the volume of the shape PQRS will be given by the magnitude, because of course volume is a positive number, dot V U dot V cross W. Okay. Now there's 2 different ways to calculate the vector triple product. We can first of all calculate what V cross W is and then dot it with U, or we can calculate it directly. So let's take a look at those 2 different methods. First of all, calculating V cross W. So again, in the same method as before, we're going to calculate the determinant of a 3 by 3 matrix made up of the components of ijk and the components of v and w. So calculating this a little bit more quickly than we did before, we've got I times 4 times 5 minus 0 times 6 minus j times 2 times 5 minus 6 plus k vector times 0 minus 4. So that's going to be equals to 20 I vector minus 10 j vector, sorry, that's minus 16 j vector plus 4k vector. So then u dot the cross product magnitude will be given by the dot product of u with the vector we've just calculated. So that will be minus 3 times 20, the first component of u multiplied by the first component of v cross w, plus 0 times minus 16, the second components, plus 5 times 4. So that will give us minus 60 plus 20, give us the absolute value of minus 40, which is 40. And again, we're just taking the absolute value because the volume has to be a positive number. So that was the first method for calculating the vector triple product, which we can use to interpret as the volume of PQRS, the parallelepiped. Now let's see the other method. This time we're going to calculate directly u dot v cross w by calculating the determinant of a 3 by 3 matrix with the components of u across the top, the components of v in the middle, and the components of w in the bottom row. So you see that all I've done there is I've put in the components of u there, the components of v there, and the components of w there. And now I'm going to calculate the determinant of this matrix. So I've got minus 3 times 20 minus 0 plus 0 times 10 plus 6 minus 5 times 0 plus 4. So that's going to give me, and of course I'm going to take absolute value of all that. So that's going to give me minus 60 plus 0, that's a plus 20. So that's equals to absolute value of minus 40, which is 40. So the volume is 40. So now let's take a look at kinematics, which describes how a particle travels through space. So we can think about the position of a particle being described by a vector, and then we can ask what's its velocity and what's its acceleration. So we've already seen an example of a vector representation of a path through space. That's when we had the parametric equation of a straight line. We wrote that the x position was equal to the starting value of x plus b1 times t. The y position was the starting value plus b2 times t, and the z position was the starting value plus b3 times t. And we saw that we could actually write that as a slightly more compact notation. R vector of t was equal to a starting vector plus a direction times t. So here we're thinking about r of t with, as a vector, with three components, x, y, and z, and those components themselves are functions of t. So we can think of this then as the position of the particle at some time, and r of 0 here is the initial position. So more generally, of course, we could have any functions for x, y, and z, and that will describe any parameterized path through space. So we can have quite complicated paths. Once we have those expressions, x of t, y of t, and z of t, we can then calculate velocity and acceleration by calculating the time derivatives of those vectors. And remember that when you're taking derivatives of vectors, all you're really doing is taking the derivative of the components of the vector and forming a vector from those components. So let's say I have some parameterized path through space described by the vector r of t. It's given by I, j, k components, x of t, y of t, and z of t. The velocity then will be the time derivative of position. Now, of course, position now is a vector, so the velocity will be a vector. And it's made up of the time derivatives, here written as x dot, y dot, and z dot, of my position. Likewise, the acceleration is the rate of change of the velocity with time, or the second derivative of position. So that's going to be made up of the second derivatives of x, y, and z. Now, of course, we can also calculate the magnitudes of these vectors. In this case, the magnitude of the velocity is the speed. So we get a scalar from the vector velocity. Speed is a scalar, velocity is a vector. Now, one interesting thing about the velocity is that it's always tangential to the path. No matter how complicated my path is through space, my vector velocity will always point along the path, tangential to the path. So we can see that what this looks like by taking a look at very small changes in the particle's position with time. So let's think about some complicated curved trajectory through space. Here's my particle traveling along this trajectory. Let's imagine that I look at the position of this particle at some time. That's going to be represented by a vector from the origin. Here's the origin. Here's the particle's position at time t. And it's going to be represented by the vector r of t. Right? So that just represents the position of the particle at time t. Now I can also look at what happens to the particle after a time delta t. That is, what is its position at time t plus delta t. So it's located now at this point. I can again draw a vector from the origin to that position, and that vector is going to be given by r at the new time, t plus delta t. So what's happened to our particle's position during that time? Well, it switched from here to here. So I can draw an arrow connecting those two things. And I can call that vector delta r, the change in the position r. And that's a vector, of course, as well. It's got a magnitude and a direction, and it's going to be simply given by the difference between the positions at the ending point and the starting point. Now, as the time change, delta t, gets smaller and smaller and smaller, let's see what happens. Again, here's my particle's trajectory. Again, here's the starting point of the particle at time t. But now I'm looking at a smaller and smaller time, delta t. So just a little bit after t, it's moved only a little bit. So this is my position at time t plus delta t. And you can see that the change in position delta r is becoming more and more aligned along the particle's trajectory. It's coming right along the particle's trajectory. In fact, in the limit of delta t becoming infinitesimally small, delta r will be aligned directly along the particle's trajectory. Of course, delta r will be infinitesimally small itself, but the velocity will not, because the velocity is defined as the rate of change, the limit as delta t goes to 0 of the change in r divided by the change in delta t, and that will be a finite number. So you can see that the velocity will always be directed along delta r, which is always directed along the particle's trajectory. So no matter how complicated my trajectory is, the velocity vector will always point along it. Now that's not true for the acceleration vector. The acceleration vector can point in any direction. It depends upon the curvature of the particle's trajectory. So we can't say anything about the acceleration vector in general, but we can say something about the velocity vector. However, in the special case of circular motion, there is a relationship between the acceleration vector, the velocity vector, and the position vector. So this is an example that you should be familiar with. We want to plot the particle's path traveling on a parametrized vector equation looking like this, cosine ti plus sine tj. So let's sketch what that looks like. You notice that my x of t, in this case, is going to be given by cosine of t, and my y of t is going to be given by sine of t. So we can see that this is a circle by simply squaring these and adding them together. So x squared plus y squared is equal to cosine squared t plus sine squared t, which is equal to 1. So this is a unit circle centered on the origin. So we've got our x and our y. And we've got our circular motion. Of radius 1. So let's take a look at what a particular point on this trajectory would look like. So let's draw our r vector. So this is the position of the particle at time t. So r vector is equal to cosine of t, I vector, plus j sine of t. So you can see by looking at that the time t is the same as the angle between the x-axis and the radius there. Now let's take a look at what the velocity would look like. That's the first derivative. So the velocity is the first derivative of the position. So I'm going to calculate the time derivatives of each component of my position vector. So the derivative of cosine of t is equal to minus sine of t. Derivative of sine of t is equal to cosine of t. And so that's going to be a vector pointing along my trajectory. So it's pointing perpendicular to my radius. So let's just check that. The velocity dotted with the radius is going to be minus sine of t cosine of t plus cosine of t sine of t, and you can see that those will cancel out. So my velocity and my radius for circular motion are perpendicular to one another. Now what about the acceleration? So let's calculate what that would be. So I'll use purple for acceleration. So acceleration is the derivative of the velocity. So that's going to be given by derivative of minus sine is minus cosine of t. Derivative of cosine is minus sine of t. And so you notice that this is actually equal to minus r. It's minus the radius vector. So it's pointing straight back at the origin. So that's always the case for circular motion. We always have acceleration back towards the center of the circle. This is known as centripetal acceleration. Okay, let's take a look at a very similar example, example 5, where again I've got circular motion, cosine I plus sine j, but you notice that there's an extra factor of 3 in there. I've got the cosine of 3t and the sine of 3t. So I want to know, how does this differ from the previous example? Well, let's see, does the radius change? Well, let's just check that. So I've got x of t is equal to cosine of 3t, and y of t is equal to the sine of 3t. So x squared plus y squared is equal to cosine squared 3t plus sine squared 3t. So it still equals to 1. So you notice that we still have circular motion with radius 1. So that hasn't changed. This is still a radius 1 circle, where the position vector is given by cosine of 3t, sine of 3t. So what is changing here? Well, let's calculate the velocity to try and see if we can understand what's changing. So the velocity is going to be given by the derivative of the position vector. So that's going to be minus, pull out that factor of 3, sine 3t, and 3 cosine of 3t. So again, I've pulled out that factor of 3. So you notice here that what's happened is that my velocity is larger now. It's 3 times larger. I've got this extra factor of 3 in front. So the velocity vector is still pointing perpendicular to the radius. It's pointing tangential to the particle's path, as it must. It's 3 times larger. So what that means is that I'm basically rotating faster and faster around the circle. It's rotating, in fact, 3 times as fast. I could also calculate what the acceleration is. So the acceleration is the derivative of the velocity. So that's going to be given by minus 9 cosine 3t minus 9 sine 3t. So you notice that I've pulled out factors of 3 again. And you can see that I get a minus 9 times my position vector. So it's pointed back towards the center of the circle again, but it's 9 times larger this time than the radius vector. So this time the centripetal acceleration is also larger. Okay, so let's take a look at a more complicated example of a particle trajectory. R is equal to cosine ti plus sine tj plus t times k. We want to know what this path is. Now, just looking at the x and the y components, that looks a lot like a circular motion, right? It looks like particle rotating around a unit circle. But that's only in the x and y direction. In the t direction, in the k direction, we've got this factor t. So let's see if we can understand what that is doing. So I've got x of t is equal to cosine of t. Y of t is equal to sine of t. So just by inspection, we can see that this will be a unit circle in the xy plane. But what about the position z of t, in the direction z? So this is equal to t, and we can see that that's linearly increasing with t. As I increase t, my position is increasing with t, which means that I have a constant velocity in the z direction. So we have this circular motion in the xy plane, but we're moving vertically with constant velocity. So that's going to stretch out my circle into a spiral or a helix. So let's sketch what that would look like. So here's my z direction. I've got x and y. And I've got a particle trajectory that's spiraling up around the z-axis. So this is known as a helix or a spiral. And we can calculate what the velocity and acceleration along this trajectory are. So the velocity, as always, is the derivative of r with respect to t. So it's going to be given by derivative of cosine, derivative of sine, and the derivative of 1. So you see that again we get circular motion in the xy plane. This is what the velocity vector would be doing for circular motion, but we get a uniform or constant velocity in the z direction. So let's see what the magnitude of the velocity would be. So the magnitude of the velocity is equal to the square root of the square of its components added together. So we end up with sine squared plus cosine squared, which is going to give me 1 plus 1, so I get the square root of 2. And notice that that doesn't depend upon t, so the velocity magnitude, the speed, is constant in time. What about the acceleration? Let's calculate that. So I've got the acceleration is going to be given by the derivative of the velocity vector with time. So I get minus cosine t minus sine t. So once again, I get circular motion in the xy plane. But then I take the derivative of this thing with respect of the z component of the velocity, which was 1. And the derivative of that is just 0. So I don't have any acceleration in the z direction. Of course, I've got that constant motion in the z direction. So the magnitude of my acceleration vector will be, again, the sum of the squares. So I've got minus cosine t all squared plus minus sine t all squared plus 0 squared. So I get the cosine squared plus sine squared, I get 1. So I get the square root of 1, which is 1. And again, that doesn't depend upon time. Now, one of the things that we saw in one of the lectures in the last topic was this very important idea that the gradient of a scalar field, grad phi, at a particular point, always points perpendicular to the level surface at that point. So where the scalar field phi takes a constant value. So now we're able to prove that using some of the ideas we've developed in this lecture. So what we're going to do is we're going to imagine we have a scalar field phi, and I've got some level surface, phi is equal to c. So let's imagine that that's some sort of rubbery sheet in three-dimensional space. It's got some sort of behavior like that. And we'd like to imagine that we take a path, parametrically defined path, that lives on that surface. Okay, so it doesn't have to be a straight line, it could be a curvy path, but the point is that it lives on that surface. At every single point along the path, we're on the surface. So we want to define that path parametrically, and we do it by writing down parametric vector equation for that path. So in other words, at every point along the path, I have an expression r of t, a vector r of t, which is made up of components x of t, I vector, plus y of t, j vector, plus z of t, k vector. Now, I know that on this particular surface, my scalar field has a constant value, right? So that's how I defined this. It was a level surface of phi, which means that phi was equal to c everywhere along that path and everywhere on that surface. So if I take the derivative of phi along my path, what's it going to be? Well, think about it. If I'm at this point, my value of phi is given by c, right? It has to be c because I'm living on this plane, on this surface. As I move along here, I'm changing my x's and my y's and my z's, but I'm not changing phi because, again, I'm still on that level surface. So phi is a constant along this path, which means that d phi dt will be equals to 0. D phi dt equals to 0 along the path. But of course, phi is a function of x, y, and z. And along that trajectory, x, y, and z are functions of t. So I have a function of a function of t. So I can use the chain rule. So d phi dt will be given by the chain rule, d phi dx times dx dt plus d phi dy times dy dt plus d phi dz times dz dt. And notice that I've used the ordinary derivative sign, a regular d, for dx dt, dy dt, and dz dt because they are each functions of t only, but I've got partial derivatives for d phi dx, d phi dy, and d phi dz. So that's my expression for d phi dt using the chain rule, but of course d phi dt is equal to 0 along that trajectory. Phi is a constant. So you notice here that that looks a lot like the definition of a dot product. In fact, I can rewrite this as the dot product of two vectors. The vector of components d phi dx, d phi dy, d phi dz, that's just the gradient of phi, and the vector of components dx dt, dy dt, and dz dt. Well, that's just the velocity field, the velocity vector. So what we've shown here is that the velocity vector is perpendicular to the gradient vector, right? So the velocity and the gradient vector have zero dot product, which means that the velocity and the gradient vector are perpendicular to one another. But the velocity vector is always pointed along the path, and that means that a vector in the plane or in the surface is going to be perpendicular to the gradient of phi. Now, since this is true for any path in our scalar field, in our level surface, that means that the gradient of phi is perpendicular to every possible tangent vector on the level surface, which means that the gradient vector is always perpendicular to the level surface at every point. Now that's the formal proof, but we can actually show it a little bit more intuitively by looking at an example. So let's take a look at the next example, example 7. So we have a scalar field, x squared plus y squared plus z squared. You can see that the surfaces of constant temperature T, or scalar field T, will be spheres, right? They'll be spheres of radius T. So we're going to imagine that we have a path on that surface. X of t equals to 5 cosine t, y of t is equal to 0, and z of t equals to 5 sine t. So let's write that out. So I've got my r vector is equal to 5 cosine of t, I vector, plus 0 j vector, plus 5 sine of t, k vector. So you notice that this is actually circular motion around a circle of radius 5, and it's in the ik direction, so it's in the xz plane. So that's a parametrically defined path on a level surface for t is equal to 25, and it's going to pass through the point 3, 0, 4. So we want to show that the velocity vector along the path is perpendicular to the gradient. So we need to calculate what the velocity vector is. So our velocity is the derivative of r with respect to t, so that'll be minus 5 sine of t, I vector, plus 5 cosine of t, k vector. And we want to know what the value of t is, right? Because I want to look specifically at the point P304. So you notice that I'm not actually given what t is. So what I'm going to do is I'm going to substitute that into my expression for r of t. So remember that x of t is equal to 5 cosine t, and we're interested in what value of t gives me the first coordinate of p, so that's equals to 3. So in other words, I get cosine of t is equal to 3/5. I also have that y of t, z of t is equal to 5 sine t, which is equal to the z component 4. So that gives me that the sine of t is equal to 4/5. Notice that I always have that the position vector in the y direction is equal to 0. So that doesn't tell me anything new. Now I could try and solve that using an equation, using a calculator to figure out what t is, but in fact all I really want are cosine and sine of t, because that's what the velocity vector is made up of. So the velocity vector is equals to minus 5 times the sine of t, and we've just shown that that's 4/5, I vector, plus 5 times the cosine of t, which is 3/5, j vector, k vector. So that's going to be equals to minus 4I vector plus 3k vector. So that tells us what my velocity vector is. Now let's calculate the gradient. So my gradient of t is equals to, t was x squared plus y squared plus z squared, so I've got 2x I vector plus 2y j vector plus 2z k vector. So the gradient of t at the point P will be 2 times 3 plus 2 times 0 plus 2 times 4. So finally, I just need to prove that the gradient and the velocity vector are perpendicular to one another. I just need to calculate their dot product. So I've got 6 times minus 4 plus 0 times 0 plus 8 times 3. So I get minus 24 plus 24, which is equal to 0. So this means that the velocity vector is perpendicular to the gradient vector. So this is actually a figure showing this. The surface in blue here is our level surface when t is equal to 25, so you can see that it's a sphere. The trajectory is shown in pink, so this is the trajectory around the sphere. You notice that it's in the xz plane. Its y value is always equal to 0. And the little pink arrows there are indicating the velocity at different points. So here's the velocity. Notice that it's always tangential to the trajectory, and it's always tangential to my level surface as well. And then at each point here in red, I've shown the gradient vector at different points. And you can see that the gradient vector is always pointing outwards. It's always pointing perpendicular to the velocity vector. And so it's always pointing perpendicular to the level surface at